lesson today will be on the wave equation. The wave equation is the equation that shows the relationship between the velocity of a wave, the frequency of a wave, and the wavelength of a wave. So it can be generally defined as that equation relating velocity, frequency, and wavelength of a wave. Now, from the definition of velocity, we know that velocity is displacement over time. Displacement denoted as x and time denoted as t, with units being in meters per second. So the formula for velocity can be gotten, which is x over t, being displacement over time. Now, for the frequency of a wave, remember that the frequency was defined as the number of oscillations made per second, from which the formula can be derived as number of oscillations denoted as n over time taken denoted as t. So the frequency can be gotten from the formula n over t, with units being hertz. And like we said, that the frequency is the inverse of the period, and the period is the inverse of the frequency. But we know that the period of a wave is the time taken to make one complete oscillation. So period can be gotten from time taken over number of oscillations made, which is exactly the inverse of frequency. And period has the same unit as time, that is seconds. Now, for one oscillation, it means n is 1, the time is 1 second. So for one oscillation, t, that is time, becomes period, and x, that is the displacement, becomes the wavelength. So from our formula of velocity, which is displacement over time, it means for one oscillation, the velocity will become wavelength over the period. Just like wavelength times 1 over t. But 1 over t is equal to f. So we can have our v from wavelength times f, which brings us to our wave equation, being v is equal to f lambda, that is frequency times wavelength. Below, from all the 4 equations we've derived that are summarized below, the equations will be very useful in all the calculations we will be doing under waves. Velocity being frequency times the wavelength, or displacement over time, frequency being 1 over period, and time being 1 over frequency. Now, let's take our first example. Take your time and look at the question. Read the question very well. The question says, an empty can is observed to rise and fall once every seconds as the wave, whose crests are 20 meters apart, pass it. I take it again. An empty can is observed to rise and fall once every 5 seconds as the wave, whose crests are 20 meters apart, pass it. Calculate A, the frequency of the wave. B, the velocity of the wave. Take out some time and think about what you've been asked to calculate, taking into consideration what has been given to you and what you need. Now, from what has been given, they said the can rises and falls once every 5 seconds. This means it takes 5 seconds for it to rise and fall down, meaning it takes 5 seconds for it to make one up and down movement. And so it gives us the period to be 5. Remember, period is the time taken to make one complete oscillation. And if it rises up and down every 5 seconds, it means it takes 5 seconds to make one up and down movement. Now, they said the crests are 20 meters apart. Wavelength is the distance from one crest to the next, or from one trough to the next. So this 20 meters given gives us the wavelength. And now, from the period and the wavelength given, how can you get the frequency? Remember the 4 equations given under waves. What of the equation can you use to calculate the frequency? From F equal to 1 over T, we have been given T. So we go straight to substitute T as 5. And we have frequency to be equal to 1 over 5, which gives us 0.2 Hertz. The B says we should calculate the velocity. Which of the equations will you use to calculate the velocity? Remember, the velocity has the equation of displacement over time. It also has the equation of frequency times wavelength. But the wavelength has been given, and we have calculated the frequency. So, from the wavelength and the frequency, we can calculate our velocity, which is frequency times wavelength, giving 0.2 times 20 equals 4 meters per second. Example 2 says, the wave troughs seen in a ripple tank are 2 meters apart. Take note, are 2 meters apart. And the frequency of the wave is 10 Hertz. What information has been given to you? The wave troughs seen in a ripple tank are 2 meters apart, and the frequency of vibration is 10 Hertz. And now we go on to ask, calculate the speed of the wave. Calculate the spacing between the troughs if the vibrating frequency is tripled. Going to A. They said the troughs are 2 meters apart. What does 2 meters stand for? The frequency has been given as 10 Hz. The distance between one trough and the next gives the wavelength, and the distance between one crest and the next gives the wavelength. Do not forget. So, the 2 meters gives the wavelength of the wave, and the 10 Hz gives the frequency. So from there, we can go straight to apply our formula of velocity equal to frequency times wavelength, giving 10 times 2, which results to 20 meters per second as the velocity. Now, the B says if the frequency is tripled, meaning the initial frequency is tripled. So the new frequency is now the previous frequency times 3. So our new frequency will be 10 times 3, which gives us 30 Hz. We go straight with this same 30 Hz and the wavelength of 2 meters. We have the velocity equals frequency times wavelength. But now, we are not looking for velocity. What we are looking for is the spacing between their troughs. Remember, the spacing between their troughs, that is the wavelength of the wave. The spacing between the troughs means the distance between one trough and the next, and that gives the wavelength of the wave. So from our equation of velocity equal to frequency times wavelength, we make wavelength the subject of the formula, which gives wavelength equals velocity over frequency. Remember, we calculated the velocity to be 20 meters per second. So our wavelength will be 20 over the new frequency, which is 30. So the new wavelength of the wave will be 20 over 30, giving 0.67 meters. What difference can you make out between the new wavelength and the previous wavelength? Remember, the original wavelength of the wave was 2 meters, and we've calculated the new wavelength to be 0.67 meters. You can see that as the frequency has been increased, that is tripled, the wavelength has been reduced. This is to say, frequency and wavelength are inversely proportional. If one increases, the other automatically reduces. That is why the frequency being tripled affected the wavelength, and the wavelength reduced from 2 meters to 0.67 meters. Let's take our next example. The next example says, a bird flaps its wings back and forth 100 times each second. I take it over. A bird flaps its wings back and forth 100 times each second. What is the period of the wing flapping? If you remember the definition of a period, then this will be very easy for you to calculate. Remember, we said Period is the time taken to make one complete oscillation. It could be vibration. The time taken to make one complete oscillation or vibration. But now, 100 vibrations are made, or 100 back and forth movements are made in 1 second, meaning the bed took 1 second to make 100 back and forth movements. This back and forth movement can also be termed as oscillation or vibration. This is to say, the period will be time taken over number of oscillations, and the time taken is 1 second to make 100 oscillations. So it gives the period to be T over N, which is 1 over 100, giving us 0.01 seconds. Taking our last example for the lesson today, an athlete runs round a football field 50 times in 10 minutes. What is the frequency of her pacing? An athlete runs round a football field 50 times in 10 minutes. What is the frequency of her pacing? Remember, frequency is N over T. That is number of oscillations over time taken. How many oscillations are made? Or how many complete cycles are made? The athlete going round the football field 50 times means she makes 50 oscillations, 50 complete cycles in 10 minutes. So our N here will be 50. Time is 10 minutes. Converted to seconds gives 10 times 60 seconds, which gives 600 seconds. And our F will be given as 50 over 600, which gives 0.08 Hertz. Now, our lesson ends here for today. I believe with the 4 examples, each and every one of you has now understood which equation to use when frequency is needed, or when period is needed, or when velocity is needed, or when wavelength is needed. We shall end our topic with graphs. That is, in the next lesson, we shall see how to use graphs to calculate problems under waves.